presentation will be primarily focused on, say, a proposer's guide for using Mustang or observing with Mustang, and not too focused on actual observing or end processing, but just what you need to know to have an idea if you are at all interested in using Mustang. All right, let's see. Can everyone see what I'm sharing?
Yes.
Great. Great. Well, then I will jump into it. And obviously, the first thing I'll start with is what is Mustang 2? So it is a 223 element focal plane array. Its detectors observe a continuum band between 75 and 105 gigahertz. The bandpass response, including Roux's efficiency of the GBT, is shown in the lower right there. And then attributes in terms of angular resolution and instantaneous field of view are given here, roughly 10 arc second resolution and a little over 4 arc minute instantaneous field of view. So it'll be helpful also just to think about what science has already been proposed for observations with Mustang 2 in terms of getting a handle of whatever you might want to observe fits what's been already proposed, or it may not be, but Mustang 2 might still be the right instrument for you. So here's the breakdown of, rough classifications that I've come up with for proposals that have been submitted, down to planetary, be it extrasolar Oort clouds or observations of our own moon. There have been a fair number of star formation ISM proposals, either within our own galaxy or extragalactic. There's only been one proposal about AGN and hyperwinds. And then by far the bulk of the science being proposed for deals with galaxy clusters. And this is observations through the Senyev-Zildovich effect, which I can touch loosely on, but won't be the primary focus of this talk. So in terms of what you're actually observing with these different science categories, it largely comes down to, I'd say, 4 different emission or scatter mechanisms. So you have thermal emission as one. Let's take the upper right plot. You see a dashed line for thermal emission. Then you've got free emission. On this plot, it's shown as dot dashed. And then, okay, long dashed lines are synchrotron emission there. But depending on the characteristics of the object you're looking at, you could have any of those 3. Then for something like AGN or galaxy clusters, you have this Synev-Zildovich effect. And so that's inverse Compton scattering of cosmic microwave background photons. And the distortion is shown in the lower plot as a function of observing frequency. And there's some dependence on the temperature of the electrons. So you see that at 90 gigahertz, where Mustang operates, you would observe a decrement. All right. Then the other thing to consider is, what is the size of the object you're going after? And does it match the characteristics of Mustang 2 on the GBT? So typical sizes of objects that have been proposed for range from generally arc minute scale to a degree scale. Although it's a bit difficult, as I'll go into later, to fully recover scales that are beyond Mustang's instantaneous field of view. That said, it is doable, as can be seen from this image of the moon that we took. All right, so why is it that scales beyond the instantaneous field of view are difficult to recover? Well, that relates heavily on how we observe with Mustang 2. So here I'll get into kind of our standard scan pattern observing strategy with Mustang 2, especially for galaxy clusters that are only a few arc minutes in radius. In which case, we use this Lisa Jude daisy pattern, which its radius is roughly that of the galaxy cluster. And so the plot here, the black lines are the trajectory, and I have some dashed lines showing the field of view of Mustang 2, listed as M2, and Mustang 1 was the predecessor instrument, which had a much smaller field of view. So you see our instantaneous field of view is, well, much smaller than the total area that we'll be surveying. And then a bit of an aside from just the scales that we cover, we also generally would like to scan fast. That just helps with atmospheric noise, but there are limitations of the structural integrity of the GBT, especially the feed arm. And so now to really get into why recovering scales beyond the instantaneous field of view is difficult is that the basic data processing strategy is to remove a common mode across the detectors, right? We have over 200 detectors, and the majority of the signal that they're seeing is the atmosphere. So in the plot here, I've shown all 223 time streams is what we call them, data that's recorded at a fairly high frequency. It's 2 kilohertz, something like that, is at least what we read it in as. Natively, it's stored at even higher frequency. And then I've just highlighted one detector time stream in black there. So the point is, really all of that signal that you're seeing is due to the atmosphere, and we want to subtract that off. So you calculate a mean across the detectors and subtract that off. Now, as it happens, we've taken to doing some additional Fourier filtering before calculating a common mode. So I show that in blue. And then finally, your red time stream is common mode subtracted and Fourier filtered. And ultimately, that's what we like to see is something that looks fairly flat and has roughly white noise properties. It turns out, though, by doing this, you are subtracting scales outside of your instantaneous field of view. Here's another way of perceiving this. If you like to think in wave number space, perhaps Fourier space, transfer functions, we quantify them for our data processing. And if we're wanting to fit some kind of a model to our data, we use these to fit to our observations. So you can just see that Mustang 1 really was losing scales, large scales. And our traditional processing method called MIDAS still is losing somewhat large scales, whereas the newer method, Minkasi, is doing the best. So why is Minkasi different? Well, it doesn't actually go through that approach of calculating and subtracting a common mode. Instead, all the data processing is maintained in time space, And instead we model noise in Fourier space. Okay, so not time space, but not map space is really fundamentally what I'm getting at. And then you can either fit some simple model to your source. For galaxy clusters, we do spherical clusters. Or if you want a map, you can treat each pixel as an element to be fit, but there are too many elements to have an exact solution. So we do a preconditioned conjugate gradient. Um, but ultimately, the real takeaway is that you're doing really all the processing and map making in time space. Okay, so here's an example of the difference between the two methods. On the left is a traditional data processing method, MIDAS, and on the right is Minkasi. So you can see that a galaxy cluster, which is shown as this decrement, the dark area, uh, its say characteristic radius is about 5 arc minutes, which is about the size of this map. So pretty much to the very edge where it's very noisy. And so even though the signal is quite weak at the edge, we should expect that overall there's a slight negative value at those large radii. But in the traditional method, you actually see right here a positive ring about halfway out, and then it's maybe close to 0 at the large radii. Here's another way of looking at it, radial profiles of the signal that we're recovering, surface brightness. So the blue is showing you recover a negative signal out to large radii, whereas MIDAS has effectively a ringing to it. Now here's a map that's 1 degree square coming from Adam Ginsberg's recent paper on the Mustang Galactic Plane Survey. And you see that it is recovering fairly large scales. There's certainly some ringing around bright objects. Notice the color scale is inverted here. Black is very bright. Uh, White would be actually a bit negative. But yeah, we do a good job of recovering large scales, and there's a little bit of room for improvement yet with this new method. All right, so I'll step back from data processing and get to a more fundamental quantity that you might be interested in as an observer, which is, sensitivity, basically. Now, it depends on the scanning strategy that you want to employ for your observations. But given that almost all of our observations go with a Lissajous pattern of roughly 2.5, 3 arc minutes in radius, uh, we've been happy to put out this number in a mapping speed based on that scan strategy for observers to use. So 56 microjanskis per beam in an hour. And you can easily scale that based on how long you want to observe if you're using that scan strategy. If you wish to use a different scan strategy, we can work with you on calculating what the mapping speed will be for that. You can also roughly extrapolate from the scan pattern what it might be. In particular, I should say that the 56 microjanskis per beam applies to that inner 2 arc minutes where the weight is fairly uniform. So you are spending time outside of that region, which does count to your overall sensitivity or mapping speed, but depending on your scan strategy, its contribution will be different. So knowing that about a third of the time is within that inner 2 arc minutes, you could figure what it would be for a different scan strategy. However, there's a slight nuance in that the faster you go, the better off you are. So it turns out the difference between a 2.5 and 3 arc minute scan strategy is actually very minimal. Even if you're spending slightly more time outside of that inner 2 arc minutes, you're scanning faster and that improves your noise properties. Okay. Then if you just want to think a little bit less about sensitivity and what's required in terms of getting the data, getting the raw data, processing it, and finally getting a map that you can use, I'll go through that. So availability of proposing for Mustang 2, it is available for anyone to propose. It is considered a shared risk instrument. Formally, it requires approval from the Mustang team. That just lets us go through the calculations of sensitivity and thinking whether that project is feasible. And again, the upshot though is that we will help you with the technical aspects. We want to see proposals go in and science come out just as much as you do. So in terms of actually when it's observing on the sky, we need the colder months when water in the sky is not so much. So that's generally October through May. It just depends on when Mustang gets put on the telescope and weather cooperating. We like to give a minimum of 30 degrees elevation just so you're not looking through that much atmosphere. If you absolutely need to observe a low deck object, you could push it down, I would say, to 20 degrees, but you are dealing with additional noise then. Those requirements tend to restrict your objects to right ascensions between 4 and 20 hours. Certainly, there's some dependence on your declination again. And then, in large part, we're competing with Argus for high frequency time. And I'd say it's roughly half and half between Argus and Mustang for the available high frequency time, which is roughly 300 hours per year or 150 hours per semester. All right. So getting even more into what it is to observe with Mustang and being an observer, it used to be that the Mustang team did all the observations, but we've streamlined a lot of the tasks needed for observing such that really any astronomer with a little bit of training should be able to do the observations. The instrument team still does the setup. That's a bit technical and rarely does it pay off to add that training to an observer's training. As for observer training, well, over the past year, people would come to Green Bank and either myself or Wilson would have been there and helped train the observer. Potentially that becomes remote, but that's not a problem either. The Mustang team is well-versed in remote training and remote observations. And of course, everyone here will know that the GBT is scheduled dynamically, so roughly 48 hours in advance, you get an email that your project has been scheduled. Then processing the data, that is handled by the Mustang team. That includes calibrating the data, making maps, quantifying the beam shape, and quantifying a transfer function. Once you have once a map is produced and a transfer function and beam shape, we send those off to the PI and try to answer any additional questions they might have, but otherwise we're leaving the analysis to the PI. All right, that's my overview. So it's pretty quick, but I'm happy to take additional questions.
Say, Charles, this is Jay.
Yep.
Going back to your very first figure of the bandpass, where you folded in the ruse correction, is the atmosphere in there as well?
Yep.
Okay. Why the ruse? That seems to be not all relevant to the kind of science that the thing does.
I'm not sure I follow why it wouldn't be relevant.
It's the point source gain. And you're not observing point sources.
Well, the thing is we calibrate off of point sources. So in terms of getting our calibration, we do need to account for it there.
Okay.
Yeah. Okay. That's a valid point in terms of the actual observations of galaxy clusters or extended objects.
So just a question about that. When you do your calibration on, say, a galaxy cluster, do you fold in the spectrum of the SCE?
Yeah, yeah.
So you're always working with things whose spectrum you know. I guess that's the saving grace.
We try to. I mean, if we know the spectrum, I can look again at Adam's paper. Obviously, he has a fair bit of supplemental data, and he listed. Well, I mean, I did the calculations for the central frequencies of Mustang 2 depending on your spectral index. But I think there could be cases where yeah, there definitely are cases where we don't know the spectrum. So we might know it for galaxy clusters, but there might be a central source which maybe isn't detected in NVSS or FIRST, and we can be pretty confident it's synchrotron, but if it's just a really faint source, we get down to tens of microjanskis. I mean, 10 microjanskis even. We just might not have lower frequency data and might not know its spectrum. But ultimately, that's not the science we're after. So we mostly just care about fitting the point spread function and subtracting it. So I guess ultimately when we care about the flux of a source, we probably do always have some idea of its spectral index.
Mm-hmm. Yeah, I mean, you just have such an enormous bandwidth here that everything is changing across it.
Right, right.
Okay, thanks.
Yep.
Oh, wait, well, I still have the mic unmuted. That map by Adam Ginsberg,
Sure.
that was Galactic Center, correct?
Is this one? I am inclined to agree. I have forgotten which the fields were, but
I can't see.
that's quite possibly Sagittarius B2.
Yeah, that's the galactic center. And then the long vertical feature is the radio arc.
Okay.
Yeah.
Yep.
Okay, so that was maybe at most 25 degrees elevation.
Right, right. So 25 was okay for us, but I mean, we had to push it there, right? There's just no chance to get it
Right.
higher. So it's doable, but uh, let's see. I should pull up Adam's paper. I can pretty much guarantee you, if the noise itself isn't higher in that map, the mapping speed is slower.
Yeah, I'm not challenging the data. I'm just saying that your poster child has actually been observed below 30 degrees.
Sure.
Yeah.
That's a fair point, but it's a lot easier. I mean, not just for us, but even the PI. If your object does rise above 30 degrees, the data quality is just going to be better. Other questions?
Hey, Charles, Ron.
Yeah.
In your time series plot where you showing the common mode and of all the pixels, I couldn't understand the y-axis. Was that in kelvins or microkelvins? That one, yeah.
That is in Kelvin forward beam. So we initially calibrate the data based off of a sky dip. And then our absolute calibrations will be tied to some point source or solar system object. But this was just a quick plot, so I used the sky dip calibration.
Yeah, if that's kelvins, right? 8 Kelvin change in 8 minutes. That's not very good weather. Is that typical, do you think, or is this one of your extreme examples?
I would say 3 Kelvin is a fairly typical variation. So sure, I'd say that's fair. It's slightly noisier, but we still see, yeah, on order a few Kelvin variations on most of our scans. It's, well, I guess I don't have a really good statistics in my head, just because it's rare that I'm making a lot of the plots of the raw data nowadays. Usually we plot just the filtered data and make sure that looks good.
And then the next question is, what about winds? What do you do anything? I know at one point you guys were actually using quadrant detector data to remove the swaying of the feed arm from winds or from just the fact that you're jerking the telescope
still use
around.
quadrant detector data. Yeah, and the quadrant detectors definitely helps us. That's buried at a lower level than I tend to look at. We don't really do too much to correct for pointing offsets on an individual scan basis. We do pointing corrections or pointing observations every 30 to 40 minutes. and correct for offsets that way. But if you get a big gust of wind in the middle of a scan, we currently don't have something to correct for that. Now, again, kind of a point Jay brought up is if we're observing extended sources, that's not necessarily as big of a concern, especially if it's just a short gust. I think certainly if it's gusty throughout the entire scan, there might be other reasons that that scan gets flagged and we don't use it. Other questions? Hello?
I can hear you, but I don't think there's any, perhaps there's no more questions.
Okay. Well, I hope if any of you have any thoughts on proposing for Mustang, that you just send me an email and we could get more proposals in.
Thanks a lot.
Thanks, Charles.
Thanks, Charles.
Yep.
Yep, thanks, Charles.